Okay, so hi everybody, welcome to lecture 8. So today we'll be actually starting with our study of a new proof system model. We have now spent, I guess, almost 2 months learning about many aspects of interactive proofs. To remind you, we started with, in the first lecture, recasting NP as sort of classical mathematical proofs that are verified by a deterministic polynomial time algorithm. And then we considered interactive proofs as sort of adding 2 new resources or capabilities to the verifier. They were randomness and interaction. We also, by the way, saw how either of them alone is not very interesting, so they lead to something interesting only in combination. And so this was, the canonical picture of an interactive proof with, prover and verifier exchanging messages, the verifier running in polynomial time, flipping coins, and eventually outputting accept or reject, right? So in the next few lectures, we'll be studying a new model, which is in some sense incomparable. So here's the picture. So now we'll be considering 2 proofs where the polynomial time verifier has 2 new resources, over the classical setting. Still randomness, that is still remains important, but a second resource, instead of being interaction, there's going to be no interaction, is a so-called oracle access to the proof. Okay, so you can think about it as so query access or random access, where random access doesn't mean it's random, it's just you can sort of in the same sense as RAM. So specifically visually how it looks like is that the prover outputs basically like an NP proof, like up here, but now the verifier has a new capability that can specify an index of the proof, and it says I would like to look location, 17, and then it gets back the symbol at location 17. So the verifier has the freedom to read the entire proof, but it doesn't have to. It can just flip coins and probabilistically sample a few locations, okay? So maybe more than probabilistically checkable proofs, maybe like this is more of a, oh wow, I even have a typo up here, it's pretty annoying. Checkable. I guess K and H are pretty close. I'll fix it in the slides. You can really think about this as like, locally checkable proofs, okay? That you have the capability or you have the option, if you know how to do it, to set up the proof so you can locally check it, okay? Are there any questions so far? So far I haven't really motivated why we're going to do it. We will motivate it pretty soon. But for now, I just want to kind of put all in one, at a very high level, all the models we've seen so far, and this is the new model we'll be seeing, which I will define more carefully in the next slide. But are there any high-level questions so far? All right. So that's the picture, but let's try to define it a little bit more carefully, just once, so then we're comfortable with it. So as always, we're going to have a prover and a verifier, and like usual, the prover is going to be all-powerful for now. We'll at some point consider efficient provers, but for now it's all-powerful. And the verifier is just a probabilistic polynomial time algorithm that has access to an oracle. So you can think about it as an oracle algorithm, okay? So formally, you model this using a Turing machine with a special tape, a query tape, that the Turing machine has the ability to write a query, and magically in the next step, the answer from the oracle appears in some answer tape. Okay, you can think about it like that. But really, it's just query access to some proof string. And we're going to say that PV is a PCP system for a language L with some completeness error, let's call it epsilon c, and soundness error epsilon s, if the following holds. Well, it's basically, very similar to what you would have for NP, except that now we'll be using the notation in the superscript. We're going to put pi in the superscript to denote it's an oracle, not anymore an input. And of course, in the NP case, we don't have randomness, so now we also have a random condition. So For every x in L, namely for every true statement, the honestly generated proof by the prover, it is such that if the verifier probabilistically checks it, where the randomness is over the verifier's randomness, then it accepts with some reasonable probability. The reason why I'm not putting here either 1 or 2/3 is that unlike for interactive proofs, so usually we will be able to achieve 1 and sort of have no completeness error, but to define the class, you can't just magically make completeness error go away like it is the case, for instance, for interactive proofs. So for now, I'll just define the class with explicit completeness error and soundness error. Again, all constructions we will see will have 0 completeness error and some soundness error. The soundness is kind of what you would expect, another typo, sorry, for x not in L, and for every choice of proof, the probability, and this should be tilde, sorry, so many typos today. The choice for any choice of proof, the probability the verifier accepts is bounded from above by the soundness error. Okay, so these are kind of natural completeness and soundness conditions. And again, the key feature is that this superscript here denotes that the verifier has query access to it, and so you could imagine a situation where this proof is very long, potentially much, and reading it might take a very long time for the verifier, but the verifier doesn't have to pay for that. It just kind of queries a small number of indices and makes up its mind, with a small number of queries. And even though it looks at a small number of queries, it will have high confidence. Now, of course, we have yet to see how to construct such objects, but that is the intent of this definition. Any questions about definitions so far? It should be fairly natural to parse. We've seen at this point, between NP and IP, we should be quite comfortable with definitions of proof systems. Okay, I don't see questions. So now I'll be using PCP in a fairly loose way. Sometimes I may say PCP for the system itself, and sometimes I may say PCP for the string itself. Okay, and the way you should think about it is some sort of robust encoding of a witness, of a classical NP witness. And this robust encoding denotes the fact that the verification doesn't have to kind of read all of its imp symbols. Okay, so let's just kind of, if you think of a classical NP witness, for example, a coloring for a graph that allegedly is a 3-coloring of the graph, you really need to kind of systematically go through each of the assignments for each of the vertices, because if you don't read part of the coloring, it could be that that part of the coloring was the one violating the 3-colorability condition, and you're not going to have good confidence. So just classical NP witnesses, as is, if you don't do something to them, they're like pretty fragile. You need to kind of read all of the entries to have some decent confidence. But we'll see how to kind of do a robust encoding of them. And you can think of this encoding as some sort of encoding of computation rather than encoding of messages, right? In error correcting codes, you encode a message so that you don't have to necessarily receive the entire code word to recover the message. Here we're kind of encoding the witness, so you don't really have to see the entire witness to establish the truth of the theorem. So it's some sort of semantically meaningful encoding. Now, so this is just kind of this, let's call them the correctness guarantees, completeness and soundness. Obviously, there are some trivial PCPs, better PCPs, excellent PCPs. How do we kind of distinguish what parameters will we care about? Now, for interactive proofs, we cared about things like round complexity, communication complexity, public or private coins. We cared at several things, right? For PCPs, let's say the primary sort of efficiency measures we'll pay attention to, these are not the only ones, but the primary ones, are the symbols over which the proof is defined. This is the proof alphabet, the proof length. So this is how many symbols are in the proof. Now, typically, of course, the proof alphabet might be the binary alphabet, but not always. The number of queries, of course, we want Q to be much smaller than L, right? And the randomness complexity. So pictorially, it looks something like this, right? So the prover has written down some string that is in sigma to the L, right? That is the proof string. And the verifier receives some randomness, yay many bits, and makes this many queries to the proof and gets back answers, okay? And typically, we will generally be working with so-called verifiers that are non-adaptive. It means that they make up their mind about the entire query set, they send off the queries, get back the answers, and just decides accept or reject. It doesn't have to be like that. There are some very particular constructions of PCPs that make queries adaptively, namely you make a query, depending on the answer to the query, you decide on the next answer of the query, but by and large, almost all PCP constructions are non-adaptive. So this is as precise as we're going to get in terms of defining PCPs. Do people have questions about, syntactically, what are they? Or at least PCP systems. Okay, so today's slides are very clear, or maybe people are tired from the homework this past weekend, I don't know. Actually, I hope it was an interesting homework. Okay, so that's the definition of PCP. Now, just to kind of get basic familiarity with the definition, let's just kind of look at some special cases, some trivial settings of those parameters and kind of compare them with things we already know. So that, so generally speaking, just to kind of specify what type of PCP I'm looking at, I'm going to be using the notation PCP class square brackets parameters to say, what type of PCP I'm considering as a complexity class. So, for example, let's say that I'm studying the setting where there is no proof. Okay, so that is equivalent to saying that the verifier is not allowed to make any queries. So let's say that I consider PCP where there's not just no proof, but no randomness. What class of languages do you expect this complexity class to be? What do you think that this should equal to? So I'm saying take a PCP, and now the verifier cannot make any queries nor use randomness. What should the complexity class that correspond to this be? Oh, maybe somebody's speaking, but I'm not hearing. Maybe I didn't, just a second. Okay, I didn't have my speaker set up properly. Can you try to speak again and see if now it works?
Oh, I just did. Is this P?
Oh, P, yeah, no, and also there's another suggestion in chat. Yes, it is P. Look, because if there's no proof in a randomness, then the poor verifier is left alone, and it must make up its mind correctly, just as a mere polynomial time algorithm, right? Also, I just noticed my speaker wasn't set up properly, so I apologize if there were earlier questions that I ignored. Happy to go back to if there were such questions. Okay, let's say that I give a wee bit randomness, log n random bits. What complexity class may I get now? Still allowing no proof, just a little bit of randomness.
Is n the size of x?
Excuse me?
Is n the size of x?
Yes, generally n will be size of x, which is size of the input instance to the verifier.
Is this PPP?
It's contained in BPP, but I would say we can say something more precise than BPP in this case. There's not many options. What's inside BPP? So okay, let me give the answer is again P. Okay, this is just a stupid point. Logarithmic amount of randomness doesn't help anybody. You can just go through it yourself and then see what you would have done in each of these cases. But it is interesting because at some point it will have highly non-trivial statements where there is a logarithmic amount of randomness and a little bit and a proof. Okay, and sort of so on its own is not powerful, but when you combine it with a proof, it will be like extremely powerful. Okay, let's say that now I still give you no proof, but I give you a bunch of randomness, as much randomness as you think, as you can handle. Which class is now?
This is PPP now.
Yeah, now it's BPP, right? Because no proof, you have a polynomial amount of time and as much randomness as you want, that is just BPP. Okay, well, let's look at the other case. Suppose we have no randomness whatsoever, and I allow you as many queries as you want. Which class should this be? I see a suggestion in chat, NP. Yes, it's exactly NP because, look, if you don't have randomness, it means that your queries will always be the same. So might as well just say that the entire PCP are your queries, okay? And that's just reading basically in full an NP witness, okay? Okay, this is just like some silly examples just to get familiar with the mental image of a PCP. And, I'll just generally denote by PCP with no brackets the complexity class where I just basically put no restrictions beyond the fact that the verifier runs in polynomial time. And this means that I would be allowing the number of queries up to poly n, randomness up to poly n, and notice that because the queries, because it's a polynomial time algorithm, you can index into proof that could be exponentially large, and you could read from an alphabet that is exponentially large, because a symbol from an exponentially large alphabet would have polynomial size, right? So PCP on its own without restrictions is considering polynomial size oracle algorithms that index into exponentially large proofs, okay? This is something that is not possible for an NP verifier because it is forced to read the entire proof. So the proof must have polynomial size. But now, since you are allowed to just sort of read a few locations of a proof, the proof can actually have exponential size. Okay, so this is just some getting familiar. And, now that we have gone through one cycle of studying carefully interactive proofs, we already have a battery of questions that we could be asking to probe this new model. We could ask, which languages have PCPs, beyond NP and BPP, which we have established they are both special cases. Is it like a lot beyond NP and BPP? Do PCPs have benefits for the languages we already have, NP? Like, for instance, we saw that for interactive proofs, we didn't get such a great, interesting interactive proofs for NP languages. Could we hope, for example, for a query complexities as sublinearing witness size that would be saying, can you verify three coloring of a graph without encoding the three coloring somehow so that you don't have to read all the colors for, like the color for every vertex, right? So there's some non-trivial encoding of the three coloring. Or even further below, right? You could ask a question analogous to doubly efficient interactive proofs. For tractable languages, can we have PCP verifier that is running faster than execution, right? You could talk about zero knowledge. Are there zero knowledge for NP languages? The answer for interactive proofs was unfortunately unlikely, right? We had zero knowledge interactive proofs for things like graph isomorphism and more generally for languages that must be inside AM intersect co-AM. So we could be asking these questions here. And we'll be visiting some of these questions in the next few lectures, but just as a broad sort of in broad strokes, we'll see that more than PSPACE, like you can capture much more than PSPACE, okay? And PSPACE is already a lot, right? So this gets even beyond that. And generally just lots of good news that yes, we have PCPs for NP languages. They have benefits for tractable language in terms of sort of verifying things faster than execution. We have zero-knowledge PCPs for basically everything. So that's a lot of good news. But there should also something a little bit kind of problematic about this good news. Like, in some sense, the PC model is simultaneously very natural, but also weird, right? So this PCP verifier has oracle access to a large proof, which is, it's not necessarily like a realistic capability of a verifier. Where does the prover writes down the PCP so that the cost model of queries is justified? Do you, I don't know, shape a cloud in that side, like, to encode your PCP, and you wait for the cloud to kind of drift over to the verifier, and the verifier looks up, and then it's a cheap thing for the verifier to do. Or short of that, if you send it over the wire, then you're paying bandwidth in the whole PCP. And how can the verifier have oracle access to something received over the wire? You see, it's kind of unclear, right? So do you write a PCP on a CD, like on a DVD, and then you send it over, but still, like the DVD reader would have to like bring the head to a certain part to make the query. So the cost model is kind of abstracting a lot away. So it's mathematically very appealing, right? But there's some sort of, it's not really usable, right? So one should ask yourself, okay, like this model seems to have all these like nice features, like capabilities that we didn't have in interactive proofs. But you could say, well, you dreamed of like an unrealistic model. Like I can also dream of unrealistic models that are very useful. And then, where did we go, right? Now, something beautiful about PCPs is that despite being sort of, yes, mathematically pleasing, but sort of unclear how you're gonna kind of, let's call it, weaponize it or put it to good use, it actually has, very powerful applications. So we'll see, very, very briefly today that it leads to a relaxation of interactive proofs known as interactive arguments. It's a cryptographic notion. We'll see that later, with strong efficiency features. So it's basically, you can think about PCPs as a way to obtain much more efficient cryptographic analogs of interactive proofs. Okay, so all right, so those are like a means to an end. And also something that we will not be visiting much in this course, but there's like enormous literature on, is that PCPs on their own, without cryptography, they actually lead to hardness approximation results. So proving things that certain problems are not just NP hard to solve exactly, but they're NP hard to approximate up to some approximation factor. And the study of this approximation factor kind of hinges on sort of constructions of good PCPs. So somehow, very magically, there are this dual use, and there's others. These are perhaps the most prominent. That despite having this sort of funny model, they are nonetheless useful. And so all this kind of great progress on PCPs, can have impact in ways that maybe interactive proofs couldn't on their own themselves. Okay. Does it make sense? Like, do people appreciate that? PCP is certainly a beautifully defined model, but it's just, it's an idealization, right? So you can think about it as some intermediate stepping stone towards something else. Okay. Questions? Yes, we have questions, but there are questions from you guys. Okay, so what I want to do now is I want to say a little bit about this item 1, because it is fairly easy to describe at high level, so that at least, since we will be doing some technical heavy lifting for the next, quite a few lectures, we need to have some good motivation to do that, because we'll be going deep into sort of many new things. So to justify that, let me sort of talk about this application. And to talk about that application, I want to mention a sort of, let's say, seminal result in the theory of PCPs. That doesn't really have a name as a theorem. I like to call it delegation of computation via PCPs. Compation, wow, so many computation. All right. And the theorem is as follows. So it will take us, let's say, maybe 6 lectures to prove it. It will basically, we'll kind of work our way upwards to it. But it's a very powerful result. It says, take any language L in n time t. What is n time t? This is the generalization of NP, where the running time of your NP decider is just some function t. T could be n squared, n to the 10, n to the log n, could be 2 to the n, right? So consider languages that have witnesses of length up to t and can be verified in time t, okay? So think about it as, generalized NP. Then has a PCP where the proof length and the prover time are polynomial in t. So this is saying that you can take your witness of size t and encode it and get a PCP in polynomial time, and the encoding will have obviously polynomial size, right? So this is like an efficient encoding, up to sort of polynomial factors. So that's good. So once we have this encoding, then we'll be able to query it and verify it as well in time that is exponentially smaller. So polynomial in the logarithm of t. Okay, now of course the verifier has to read the input of size n, right? So it has some dependence on n, but this is like some fixed polynomial. I don't know, think about it as n squared or something, or quasi-linear in n. And so like the point is that there's an exponential gap, exponential speed up over like just checking things by yourself, which would be t, right? So again, without proof systems, this language requires a decider to look at a witness that has size up to t and running time up to t to figure out whether it's a good witness. For example, you can think about it as a graph of size t and you're checking a 3-coloring on a graph of size t, right? That can be done in linear time, provided the presentation is sorted already. And you're checking it with a polylog number of queries, so in some sense the amount of information read by the verifier is exponentially less, and also the checking itself is exponentially less, okay? So it's a very powerful result. So this is kind of the picture. It's a large witness, much larger than the input. Polytime, you produce this proof, has polynomial size in t. You make a small number of queries, get back the answers, small, efficient predicate, exponentially faster. And actually, when this theorem was proved, this is actually the screenshot from the paper. The authors at the time knew exactly what they were getting into. It's checking computations in polylogarithmic time. So this was, in fact, exceedingly visionary. You have a paragraph in the abstract that says, in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. So this is basically alluding to the capability that you can think of this as like a very weak machine that, it's kind of trusted, right? So it's like your local computer that with some simple software stack and simple hardware. And you have this big bulky machine that is doing some complex computation that you just don't have the time, is potentially exponentially more than your resources. And yet, in this setup, in this model, you're able to kind of gain control over it, and sort of be able to check the correctness of the computation, right? Because X could be encoding the input and output, and then the language could be talking about some correct computation of some function, right? Yeah. Are there questions about this? So I'm just stating a result that we'll be working our way up to prove. We'll see all the necessary components to prove this. It'll just take a few lectures for that. But notice also that this is still the PCP model, and the authors that wrote this paper, they really did cover themselves, because they say in this setup, right? that is an important word, right? Because how do you use this setup, right? It is true that in this setup this is possible, but it's unclear how you're going to, where you send this proof system, right? This PCP. So this brings us to this application to interactive arguments that I alluded to earlier, and now I want to sort of explain. Before I get to some very lightweight cryptography, are there any questions about the statement of this result and why this statement is non-trivial?
Why can't you just do this with an interactive proof, where the prover message is very long and the verifier doesn't read all of it?
The question was, why can't I do this in interactive proof where the message is very long and the verifier reads a small part of it? Because that's just not what is an interactive proof. An interactive proof does not consider the possibility of oracles. Okay? Now, we will see later in the course that once you realize, okay, we can have interaction and randomness, or interaction and query access, why not have randomness, interaction, and query access? And we'll see that there are ways to kind of combine benefits from both. But right now, not right now, interactive proofs just do not consider that one. That we proved all kinds of limitations on interactive proofs, such as showing that they're contained in PSPACE, or showing that sort of interactive proofs where the prover sends a small amount of bits to the verifier are not very powerful. All of those things were predicated on a formal model that said that the verifier is reading everything the prover sends. Good question. Are there more questions about this statement? Notice that this is a very powerful statement. We don't expect something like this to be true for interactive proofs, because this in particular implies, like for interactive proofs, we don't expect, for example, to have an interactive proof with sublinear communication for let's say 3-sat, right? Because that would contradict the exponential time hypothesis. So that's something that we saw a few lectures ago. Yet here, you could, for example, set this language to be 3-sat. T here would be like order of n, because the time to verify a 3-sat formula is linear, and the query complexity would be polylogarithmic. The verifier time would be polylogarithmic as well.
Here, the verifier time would be like linear, right? Because it still needs to, or...
Well, it's a great question. So it depends what is the representation of the formula. So if the formula is like random, then obviously there is no smaller representation of it. But you can imagine a formula has some structure that, what you give to the verifier is a formula descriptor rather than the formula itself. And in that case, you can indeed work in time that is sublinear in the formula size. And we will see that, because if you think about it, languages here correspond to computations of size t. But the description of that computation is just a constant size Turing machine. So that is why it is possible for the verifier to run much less than t. And similarly, or at least completely analogously, if you have a formula that has a smaller description than itself, it's basically like an algorithm that describes the formula, then the verifier doesn't have to, let's say, unroll it to kind of check it. It's a good point. More questions? Okay, so now I want to address this kind of a problem. I mean, in some sense, this really is like a missing piece of this vision of checking computations at polylogarithmic time, because this setup is not really realistic. I mean, it is an idealization of some mathematical model. It is excellent that we have something like this, but we have to work a little bit harder. It's not much harder to kind of make it useful. Okay, so this leads to a 2-slide crypto interlude, where I will sort of explain how, given any PCP, you can construct a so-called interactive argument. Now here, argument is a cryptographic terminology that says the proof system, it is secure only insofar as some specific cryptographic primitive is not broken. Okay? And yeah, I will not define it precisely, but it will be clear from whatever I'm going to show that if you consider an unbounded malicious prover, then something goes wrong. And so argument denotes this fact, that you're going to have soundness only against computationally bounded adversaries, which anyways in the real world is good enough. Not just the real world, but let's say from a philosophical perspective, that is also good enough. So roughly speaking, we're going to have a transformation that says, suppose that you give me some generic PCP that has, let's say, some prover time PT, veri time VT, and query complexity Q. All right? Then, by using cryptography that will kind of make it more precise in a moment, we can construct an interactive proof. I put proof in quotes because it's going to be an argument for L such that we basically preserve the prover time and verifier time up to cryptographic operations. So if we had a good PCP prover time and a good verifier time for the PCP, then we just don't mess them up. And the query complexity becomes communication. So that if I want small communication, okay, then all I really need to do is to have small query complexity, right? This is something that, small communication interactive proofs is something that we know are weak, right? Because we proved kind of lower bounds against them, like a few lectures ago. So in particular, if we apply this PCP to the prior slide, we get a very powerful result. You get an interactive argument. So now this is two entities that are just chit-chatting in a normal way. Send a small message, send a small message, send a small message, send a small message. How small? Polylog, right? And the prover runs in poly t time, and the verifier runs in polylog t time. So this really is like an actual protocol one can run over the wire, because you'll be exchanging an exponentially smaller amount of bits. The verifier will not be using any sort of imaginary capabilities. It is sending real messages and receiving real messages. And it is working exponentially smaller than it would have by checking computation by itself. And crucially, again, this does not contradict limitations of interactive proofs with small communication, because the security of this protocol will not be information theoretic. The soundness will hold only as long as the malicious prover is, let's say, running in polynomial time. Because if it instead, for example, was running in exponential time, it could break cryptography and fool the verifier. So now I'm going to be providing intuition for how this theorem, it's only going to be informal because this class is not a class about cryptography. And so, sort of the notion of security reductions and cryptographic notions, you may or may not be familiar with them. And so in the design of this course, I didn't want to make it an additional prerequisite on many other things that one has to catch up on. All right, so let's first do a simple proof attempt, okay? At a very high level, we want to turn queries into communication. We want to not have to have the prover send the big, long, bulky PCP over the wire. We just want to exchange messages that are proportional to the queries. Now, a naive way of doing that would be to say, okay, look, verifier, just figure out what is the randomness you're going to be using for the PCP. Me, the prover, I will materialize the long proof in my head. Given the randomness you gave me, I am going to figure out which queries you want to look at. I'll send you just those, and just run whatever check you wanted to run by yourself. Okay? So in this way, the verifier is just asking the prover to pretty please send over the part of the proof that it is interested to look at today. Can anybody point at a problem with this protocol?
Like with the PCPs, the prover has to have the whole string written out, but here the prover can kind of change their mind on what to send.
Yeah, right. So the problem is here that the prover can pick pi based on Q, right? And so this reversal of quantifiers, it is very important, right? The security guarantee of a PCP says fix the proof, then with high probability of the randomness of the verifier, kind of local views, right? This is a local view, will lead to a rejection in the soundness case. It does not say that if you first fix the randomness and therefore the query set, you cannot concoct a proof that is made to make that specific query set accept. okay? The analogy I like to keep in mind is like guessing a coin toss after the outcome is known. Of course you can do it, right? So like it's important to first say what you're guessing and then you flip the coin, right? You can't do it after, that's too easy, right? So, and also more worryingly, we haven't used any crypto. Like if this was sound, like it would be an information threaded protocol. And so even if you try to come up with something, you know, more, let's say, elaborate, if you're not using any cryptography, there's something fishy going on, because we know we're not supposed to be able to have interactive proofs with small communication, okay? Is it clear to everybody that, you know, this is a failed attempt? Good. Now, despite being a failed attempt, it is basically extremely close to what we're actually going to do. And cryptography is precisely going to address this issue of sort of choosing the PCP based on randomness. So this leads to something that is known as Killian's protocol. The rough idea is to say, look, we're going to use cryptography to make the prover first commit to the PCP string, and then we're going to locally open locations of it. In some sense, this is exactly what was happening in the PCP itself. The prover, by writing down the PCP first, it was committing itself to it. It's just, we don't like this trivial commitment of sending the PCP to the verifier, right? So we want something more shorter than that. So this brings to the notion of collision-resistant functions. This is the definition of it. We're going to say that a function family, now it is parameterized by the security parameter lambda, and this is a compressing family that sends 2 lambda bits to space lambda bits. We say that it is collision resistant if for every efficient adversary that sees a random element from this family, the probability that it outputs 2 inputs that are distinct and map to the same output is negligible in lambda, okay? In the security parameter. Now, negligible is a technical word. I won't define it. Roughly, it means it vanishes. I mean, it becomes, it's a function that becomes smaller and smaller faster than the inverse of any polynomial. So it goes to 0 faster than n to the minus 100, then n to the minus 1000, then n to the minus 1 million, faster than all of them. And this is, you know, just the standard notion of collision resistance. It just says, given a random description, of a random element from the family, you can't find any 2 inputs that hash the same output. Why collision resistance? Because this directly leads to a specific type of commitment, a so-called short commitment with local opening, all right? And that is going to be basically a preceding round before we do something like what we did in the broken protocol. So now the first message is going to be the verifier that says, okay, I'm going to sample the hash function, because, you know, you can't trust the prover to do it for yourself. So just sample it and tell the prover, hey prover, today we're going to be using this hash function. Good luck, right? The prover is going to materialize the proof, but then it has to kind of compress it. And how it's going to do it is going to use this construction that, you know, you're most likely have seen somewhere of a Merkle tree. Basically, you lay out the proof, that is the long PCP, and you pairwise hash it. Notice that we're going from, say, 100 bits to 50 bits, right? 100 to 50, 100 to 50. So you can, every time you kind of hash 2 things, you're compressing by a factor of 2. So compress by a factor of 2, compress by a factor of 2, compress by a factor of 2. You do it, you know, logarithmic number of times in the length of the input, and at some point you reach something that is known as the root of the Merkle tree. And you just send that, and you say, hey verifier, here's my root, here's my commitment to the PCP, and by the way, this is a short commitment, that's why I can send it to you. Now that the verifier has the commitment in hand, it says, okay, well, now I have the root, it is safe to send my randomness, and then we do something that is basically an augmented protocol, augmenting the protocol we were running before. the prover is going to figure out what is the query set used by the verifier on this randomness, and it will say, okay, here are the answers, and here are so-called authentication paths that certify each of these locations. Now, intuitively, kind of, let's say that the verifier wanted to read this one, that location. So what the way that a Merkle tree works is that you're going to send the siblings of every node on the path to the root. So it's going to send this one, it's going to send this one, it's going to send this one, and it's going to send this one. By sending all of these sort of, let's call them witness nodes, the verifier can kind of recompute the root by retracing the path, right? So it will kind of recompute this one, then recompute that one, recompute that one, recompute this one, and then establish that, yes, I get the same root that I was sent earlier, okay? And this Merkle tree property, because it is constructed using a hash function that is collision resistant, one can prove that the entire thing now is collision resistant. It is impossible, short of breaking cryptography, for the prover to change his mind about what he put at the leaves of this Merkle tree. Now, whatever I said sounds very intuitive. Formalizing it is actually rather non-trivial. It requires making arguments that are security arguments that are a little bit complicated, and they're like really involve like some cryptographic intuition that we're not developing in this class. So there's a question that says, does anything change since we're sending intervals of the proof versus a single point of the proof? No, we're sending single points, right? So I'm sending this is one point of the proof. This other guy, he's just an auxiliary next neighbor, but so what? Like, I wanted to send Q symbols. Now I'm sending, I was sending Q symbols, and for each of the symbols, now I'm attaching a so-called authentication path, which is pretty small. It is a logarithmic number of nodes in the tree, where logarithmic is in the proof length. So that is something pretty cheap. So I think I have it here. So if you have L leaves down here, then the amount of information you're going to be sending is, let's see, lambda bits here, right? Lambda bits here. Here is just some randomness, but randomness is, you should think about it like on the order of the query complexity or not much more. Here we have the Q queries, right? And here is like Q log L sort of outputs of the hash function, and each of the outputs is like lambda. So overall, the dominating term really is like Q log L, which is pretty small. And if you see what the argument prover and argument verifier are doing, well, the prover is just running the PCP prover and constructing a Merkle tree, which is easy. It's just saying pairwise hashing. It's a linear number of hashes. So that's like really like a minor term. And the verifier is just running the PCP verifier and checking a small number of authentication paths. It's like a very small number of so hash functions, okay?
So I guess my question was, now we're working with some hash function that has some range that's like size 2 lambda, where before we were just querying like a single point, but now every time like we take a hash, it's like over a bigger amount of the proof, right?
Yeah, and and the question was, now that the input is over a bigger amount, you can either pad with zeros, and it's really not going to change much, okay. Or you can you can bunch up the PCP into blocks of lambda, just to save. I just want to say that sometimes you may do one or the other for other reasons. For example, if you're trying to preserve the zero knowledge of the PCP, you may not want to reveal neighboring inputs that you're not interested in, because maybe your PCP doesn't have guarantees about that. We're not going to be talking much about zero knowledge PCPs, but sort of to a first approximation, it doesn't matter whether you bunch them up into blocks or you pad them with zeros or like some symbol that you can then sort of parse away. Great. The point that I want to convey this is that there is this prior round that is a cryptographic commitment by the prover about the PCP before the verifier reveals its randomness, okay? And then there's a way through this tree structure to open up specific locations, because remember, we are only interested in a small number of locations. We don't want to say, here's the whole PCP, recompute the entire Merkle tree. No, that we can't afford that. Otherwise, we would have sent the PCP to begin with, right? Here we want to reveal a small number of locations. Small parenthesis, Merkle trees are used everywhere, not just in theoretical computer science and cryptography, they're used in computer science in general everywhere. So I encourage everybody, if this is the first time you see these objects, I encourage you to read up on them because they're incredibly useful, like throughout in all kinds of systems building, and they're obviously very cheap because it only uses cryptographic hash functions. As I said, the security analysis is a little bit involved, and it's kind of beyond the scope of this class. Roughly speaking, what you need to prove is that if there is a prover, an argument prover that is efficient, actually, before we get there, notice that if the prover is malicious and has unbounded power, then it will just break the hash function and lie about, sort of opening new things, right? It will just commit to junk. Then when it sees the randomness, it will just break the hash function and open to whatever it wants. And so we're back to this broken protocol. So you really need the prover to be bounded. And so the security analysis goes something like this. If you have like a prover that runs in polynomial time and it convinces you with some probability, then you want to argue this is because there is some PCP that he's thinking about that convinces the PCP verifier with some similar probability. And you want to argue that, that can't be large because the soundness of the underlying PCP kind of forbids it. And so then you have a contradiction, right? And the technical difficulty is to kind of extract the PCP from the prover's head, because he's only speaking a small number of locations with each execution. So you need to somehow wrangle these interactive algorithms to kind of say, all right, what do you say on this randomness? What do you say on this other randomness? So you need to kind of recreate a PCP that could be he was thinking about, and it's like a not an easy argument. That's why we're skipping it, but we're going to be doing careful arguments about complexity and proof systems, but not cryptography in this course. All I wanted to say is convince you that once you have a PCP, you need just lightweight, super simple cryptography to lift it up to a cryptographic notion of an interactive proof. And you basically benefit from whatever you had good things with the PCP, they're just inherited by the interactive so-called argument. Are we clear on the motivation of how PCPs help you construct interactive arguments? By the way, technical term for this is a succinct argument because the amount of communication is succinct. So this is the canonical construction of a succinct argument. It is built from a PCP. All right. I should also say that not quite from PCPs, but related objects, these constructions are today in production, in real products that used by real people, it's sort of primarily in the blockchain space. So the fact that there is this very lightweight use of cryptography is a feature. It makes the entire thing very fast, so that it basically boils down to having very good information theoretic objects underneath. We'll study them. They're basically a hybrid of PCPs and interactive proofs. And so this very same paradigm of commit with a Merkle tree and then locally reveal is sort of used in technology today, so with so real money behind it and real customers. So yeah, and underneath all of that, there's lots of complexity theory. Any questions? Because I'm about to kind of sort of finish the interlude on cryptography and come back to sort of PCPs. Okay, I don't hear anybody. So Okay, now we're back to studying PCPs, and it's a new model, so we have to start a little bit from scratch. So we're gonna just make a couple of observations this time, and we'll start a bit more seriously sort of with constructing PCPs next time. The first thing I want to start with is let's at least put an upper bound on PCPs and their power. If you remember, for interactive proofs, the upper bound, which ended up being tight, was PSPACE. And first I want to convince you that PCPs, they're going to be upper bounded from above by NEXP. Okay? So, and just as a legend, here are the sort of complexity measures that you typically pay attention to: proof length, proof alphabet, and query complexity and randomness complexity. And this theorem comes from, it's a direct combination of two rather simple lemmas. The first one is that without loss of generality, the proof shouldn't be too long. Specifically, if your verifier is non-adaptive, then there's no need for the proof to be larger than 2 to the r times q. And if you have an adaptive verifier, then there's no need for your proof to be longer than 2 to the r size of the alphabet to the q times q. And these are just counting. I should also say that typically in constructions, the proof that you write down by engineering the proof system is a specific length because you designed it that way, and usually the length will be much less than these quantities. But this is kind of saying, in the worst case, there is really no need to be longer than that. Okay. Now for the first item, look, if you have randomness r, then there's at most 2 to the r different query sets. Okay, and each query set will have size q. So there's no need to write down a proof that is longer than 2 to the r times q, right? So that is for non-adaptive verifiers. For adaptive verifiers, it could be that your query set depends on the answer from the proof, right? So depending upon the symbol that you get in return, you might say, yeah, actually, depending on this symbol, I'll change my next query. And so that introduces an additional factor of size of sigma to the q. Okay, why? Because with each query you have size of sigma possibilities, and that may change the next one. This is not a tight upper bound; is pretty sloppy. Maybe I don't even need the multiplicative factor of q, but this is certainly good enough. All right, so this is just saying the proof. You can always upper bound it in terms of these parameters. The next thing is to say, well, if you have a PCP with a certain proof length and randomness complexity, then you can always put it in n time 2 to the r plus l times poly n, right? So what is n time? Remember, that is like np, but parameterized. And okay, well, if that's what we need to prove, give me some arbitrary PCP for some language in this complexity class, which means that the PCP verifier uses r random bits to query a proof length that consists of, let's say, L bits for now. So here is a decider that says, okay, so give me the input and let's guess as a witness a proof, a PCP proof that sort of tries to convince me. Okay, this is a PCP proof, but I'm treating it as an NP witness of length L. Okay. And internally, what I'm going to do is I'm just going to run the verifier on every possible random string, right? So for every choice of randomness, I'm going to run the verifier on this proof that was given to me as a witness. And I'm just going to accept if the fraction exceeds the probability in the completeness case. And, it's easy to see that, if X is in the language, then, the honest PCP will make this thing accept because this will add up to the right probability. And if X is not in L, then it will not, because of the soundness condition of a PCP, and I will say no. And the running time of this thing is 2 to the r times the running time of the verifier, which is poly n, plus something that depends on the proof, just to keep it around and query it, reading it off from the input tape and querying it. So just some sort of service tasks related to the proof. But look, the proof has size at most this one, which is 2 to the poly to the poly times poly. Well, that is just, exponential in n, okay? So Voila, okay? So that, this is, if this is like at most exponential in n, that is precisely NEXP, okay? Because this is non-deterministic exponential time. Let me maybe write it precisely. This is equal to n time exp in n. So, all right, so like PCPs can't give us languages beyond NEXP. Are there any questions about this argument? It's just, again, it's similar to interactive proofs, right? What did we do with interactive proofs? We said, give me a generic interactive proof. I need to figure out the accepting probability for the game tree. I can do it in polynomial space. I'm done. Here, you give me some generic PCP. I need to figure out the accepting probability for the PCP verifier. I need to, you need to give me the PCP to begin with as a witness. And then I just like run over the verifier, and then if we get the right probability, I'll say yes. Otherwise, I'll say no. And by the way, NEXP is a pretty large class, okay? So it's even much larger than PSPACE, because above PSPACE there is EXP, there is exponential time, and there is NEXP, which is non-deterministic exponential time. So it is the exponentially large version of NP. It's really an enormous class.
Does this proof use more than polynomial space?
The question is, does this proof use more than polynomial space? It sure does, because the proof length here could be exponential, right? And I need to read it in and operate on it by querying it. So I need to put it in my working memory, and every time there's a query, I need to go there and like read off whatever the verifier wanted to read. So it uses exponential space as well. Good question. Any more questions about the upper bound? Okay. So here's another, now that we have an upper bound, let's do a simple lower bound, PSPACE. Actually, with what we know, it will be basically trivial to show that the complexity class can at least include PSPACE, okay? And the dilemma is just that we can basically put all of IP inside PCP. Okay, so even though they're kind of looking comparable, there's some sense in which PCPs are kind of like, let's say, more powerful than interactive proofs. And that sense is this one, which we're going to prove right now. So, okay, well, if I have to prove this, again, give me some interactive proof, and without loss of generality, let it be public coin, okay? Now, of course, public coins, the transformations that we've seen may mess up other properties of an interactive proof, like it could mess up the honest prover's runtime, blah, 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 but right now, I don't care, right? I'm just looking at, set of languages, right? So that really is without loss of generality. And what am I going to do? I'm just going to write down all possible transcripts and just call that a proof. Okay? So here are all possible first prover messages, all possible next prover messages, second one, that's a bigger one, right? So kind of the proof is just one enormous string that looks like this, right? And here it is. And the point is that I can set the PCP verifier to just sample randomness and just read from the proof as if it was playing against some IP prover, right? And it will just, if this is R1, then it will kind of read off here what the prover would have said on R1. And then it says R1, R2, then it says what the prover would have said on R1, R2, and so on and so forth. And the point is that, for the honest prover, yeah, whatever, we can just write down what the honest prover could have done. Like that we can do. And for soundness, it's easy to see that like there's nothing the malicious prover can do to cheat. He has committed himself to his full strategy, and we're just basically simulating him playing with us. He doesn't have any new capabilities. Any proof in this format exactly corresponds to a strategy in an interactive game, because there is a message for every partial transcript. So we're preserving completeness and soundness, and so we can just basically simulate interactive proof. Now, of course, this transformation is not very nice for the honest prover, because maybe the honest prover of the interactive proof was very efficient. And now the honest prover of the PCP has to basically run the honest prover interactive proof on every possible transcript, right? But again, who cares? Right now we're just looking at complexity, sort of complexity classes. And so we're kind of discounting that right now. So remember that, when we do complexity inclusions, it doesn't mean that, this class is useless, this is more useful, right? It just says as a set of languages have these objects versus these objects. There are plenty of other comparison points about honest provers, zero knowledge, efficiency of the verifier, whatever, right? So there are many other points that, are not sort of represented by this. But as pure complexity, we can just like write down all possibilities and just let the PCP verifier simulate a play, and that's good enough. Does it make sense? So what we've learned is that as a complexity class, PCP contains PSPACE and is contained in NEXP, right? What we will see is that PCP actually equals NEXP, and will be recycling techniques like arithmetization and soundcheck. But to get there, we'll also need new ones, right? We're going to be using something known as low-degree testing. That will be the main new ingredient that appears in PCP constructions and is not present when you merely use interactive proofs. But we'll be doing a lot of recycling. That's why sort of we did all this like careful study on interactive proofs has laid a lot of groundwork because we're doing, again, a lot of recycling. And then, you say, well, who cares about NEXP, right? The point is that once we achieve that, we'll be able to kind of scale down this result back to NP and get the type of speedups that we've seen in the statement about the delegation of computation result, where for problems of interest that are tractable, we can go exponentially faster relative to the computation that we care about, right? So PCP equals NEXP is sort of like a way to force us to have an exponential gap between a polynomial size prover and exponentially large proof. Once we know how to do that, then it will be most of the way towards basically scaling everything down and demonstrating this exponential speedups for PCPs. All right. Anyway, so before I take more questions, I just got reminded, there is a spreadsheet that I put on Piazza for letting scribes sign up in advance. I've seen already some people getting scribed. We have all lectures covered in the past. There is the next lecture having has already been booked as of the beginning of this lecture. Somebody has to yet book today's lecture. So, if somebody wants to volunteer to scribe today's lecture, please email me message me on Piazza privately. And either way, you can sort of book yourself for future lectures, just not too much into the future. Let's say the next 3 or 4 lectures. Also, I have received all the homeworks. Please, for the next homework, see if you can please keep a different problem per page. It's easier in Gradescope. And, I'll be grading these things at some point. I'm pretty busy, I'll get to it at some point. But, before the end of the semester. For sure, and then most likely, sooner rather than later. But, thanks. I hope you had fun during the homework. All right, that was just some administrivia. Coming back to the lecture, that's all I wanted to say on PCPs for today. Just to come back to the sort of what we'll be working our way towards is this statement right here, that we want to be able to say that for any non-atomistic computation, we can encode the witness in polynomial time to obtain a polynomial size PCP and check it exponentially faster, okay? So this is a compression of both witnesses and computation together. All right, so this is a good time to stop the recording.